The topic of this lesson is two related data structures, generalized maps and combinatorial maps. These are rather special because they can be used to represent data of any dimension, including in 2D and in 3D. In 2D, combinatorial maps are equivalent to most half-edge data structures, which means that we can use them to store sets of polygons and the topological relationships between them. But the advantage is that by simply moving to 3D combinatorial maps, we can also store sets of polyhedra, including the topological relationships between them. As for generalized maps, they are quite similar to the combinatorial maps of the same dimension, but they avoid the concept of orientation, which simplifies many algorithms at the cost of having twice as many primitives. Let's start by introducing some concepts that are related to generalized maps and combinatorial maps. A simplex is a primitive that describes the simplest linear geometry that we can make in a particular dimension. A zero simplex is a point, a 1 simplex is an edge, a 2 simplex is a triangle, and a 3 simplex is a tetrahedron. Then, a cell is a primitive that can be used to describe a more complex object of a particular dimension. So, all simplices are cells, but any polygon would also be a 2 cell, and any polyhedron would also be a 3 cell. Finally, a simplicial decomposition is a process that we use to split cells of a certain dimension into simplices of the same dimension. Informally, we can also just call it a triangulation, but bear in mind that it can be a triangulation in any dimension. And so in this context, a tetrahedralization is also a triangulation. Such a triangulation can be done geometrically, like with a constrained or conforming triangulation, but it can also be done as a combinatorial operation without any geometric tests. Generalized and combinatorial maps do exactly this. In fact, the primitives in a 2D combinatorial map are like those in a barycentric triangulation of a polygon. Let's go through this step by step. In a barycentric triangulation, a roughly convex polygon can be triangulated by adding a new vertex in its barycenter, then creating the triangles by connecting every one of its existing edges to the new vertex. This process therefore creates one triangle per existing edge in the polygon, which is more triangles than what would be created if we had used a constrained triangulation. But unlike a constrained triangulation, this process doesn't require any geometric operations. Going back to generalized and combinatorial maps, let's show how this works with an example using the 3 polygons here. First, on the left, we have a 2D combinatorial map of the same 3 polygons, where the triangles are exactly as in a barycentric triangulation. Every triangle is made with the new vertex, which is marked with a 2, and the 2 vertices of an original edge in each of the polygons, which are marked with zeros. The number 2 is because this vertex comes from it being created on a 2-dimensional face, whereas the zeros are original 0-dimensional vertices. The triangles here are the main primitives in a combinatorial map, which are called darts. At this point, it's important to note that there's a major difference between a barycentric triangulation and the triangulation we've done here to obtain the darts in a combinatorial map. The vertex marked with a 2 is not in the barycenter. In fact, it doesn't have a real location, even if we've assigned it one here to ensure that the triangles don't overlap. Now, on the right, we have the equivalent 2D generalized map of the same 3 polygons. This structure is created by first splitting every original edge in 2 by putting a new vertex in it, which we mark with 1s because they come from edges. This operation is actually a barycentric triangulation of every edge. And then we perform the same triangulation as for a 2D combinatorial map. As you can see here, this means that there are exactly 2 generalized map darts for every combinatorial map dart. And every dart in the generalized map has a vertex marked with 0, a vertex marked with 1, and a vertex marked with 2. So, we can say that a generalized map is a unique vertex-edge-face combination, whereas a combinatorial map dart is a unique edge-face combination. Moving on to 3D, things are very similar. In order to compute the triangulation that is needed, which because we're in 3D is a tetrahedralization, we first do a barycentric triangulation of every face. This example is for a combinatorial map, but note that in a generalized map, this implied first triangulating every edge as before. After triangulating every face, we do a barycentric triangulation of every volume. For this, we add a new vertex in the barycenter of the volume, then connect it to every existing triangular face, which creates a tetrahedra. If we assign the volume barycenter vertex a number 3, we can see the pattern. A combinatorial map Dart has two vertices marked with zeros, a vertex marked with 2, and a vertex marked with 3. A generalized map is easier because it only has one vertex marked with every number from 0 to 3. So, if we wanted to store the vertices of each dart in a generalized or combinatorial map, we can see that in a generalized map, we could store them using the order of the vertices. But in a combinatorial map, there is some ambiguity because of the two zeros, which is a problem. Essentially, we need to select one of the vertices to go before the other. In order to do this consistently across all connected cells, we give an orientation to the combinatorial map. This orientation should be just as in a half-edge model, with adjacent darts having opposite orientations. Going back to the cube example from before, you can see that this graphical representation of simplices can be messy in 3D, where you can only see some tetrahedra because they end up obscuring each other. Besides, it can be somewhat misleading because we're putting the vertices marked with 2 and the vertices marked with 3 in arbitrary locations, which they don't actually have. So, when you see generalized or combinatorial maps represented graphically, the usual approach is to represent them in a simpler way by omitting most of the vertices of each dart, like the example shown here on the right. Now, let's explain what are the relationships between darts, which are better understood in terms of simplices. An n-simplex has n plus 1 adjacent simplices, which share a common n-1 simplex on their boundary. In terms of darts, then we know that a dart in an ND combinatorial or generalized map has n plus 1 adjacent darts. Then, because an n-1 simplex on the boundary of an n-simplex has all of its vertices except 1, we also know that two adjacent simplices share all of their vertices except 1. And because darts always have the pattern of vertices of different dimensions that we discussed before, when we moved from a dart to its adjacent neighbor, we are simply switching one of its vertices for another of the same dimension. This operation to switch a vertex of a dart for the vertex of its neighbor that has its same dimension is known as an involution. This term means that a mathematical operation is its own inverse, which is true here, since doing the same operation twice returns us to the original dart. In generalized maps, this is denoted as alpha I, where the I is the dimension that we're switching. In combinatorial maps, this is instead denoted as beta I. However, there is an exception here. Switching the zero-dimensional vertex of a combinatorial map dart is not an involution because this operation just means moving to the next edge on the loop of darts around a face. Because if we keep doing this operation, we eventually end up in the same dart, it is instead known as a permutation. And because this operation switches the edge where we are, it is not known as beta 0, but instead as beta 1. Here you can see an example with the 3 polygons using the simplified representation. Note how all the operations are involutions except for beta 1. Here we have another example with a polyhedron, which we can use to introduce the concept of orbits. Given a starting dart, an orbit gives us all the darts that are accessible from it, while following only certain involutions and permutations. As we have seen before, switching the I-dimensional vertex from a dart means switching the I-dimensional cell that it belongs to. Because of this, if we want to obtain all of the darts on a vertex, edge, face, or volume, we simply need to obtain the orbit that allows all involutions and permutations except for the one of that dimension. So, in the example here, the orbit alpha 1 alpha 2 gives us the dart of a vertex, the orbit alpha 0 alpha 2 gives us the dart of an edge, and the orbit alpha 0 alpha 1 gives us the darts of a face. Finally, we should mention the concept of sewing, which is the basic operation that is used to construct a generalized map or a combinatorial map. If we are careful about the way we implement an orbit, we can obtain all the darts of it in a consistent order. This means that we can do parallel traversals of different objects for different purposes, such as to compare them. But we can also use it to easily construct large objects. If we start from a couple of darts that correspond to each other on a face that we want to saw together, we can do a parallel traversal on each side, and we can connect each pair of darts with the proper involution or permutation.